This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Selected industry organizations. So for the first talk, it's my pleasure to introduce Professor Harry Quiney. He's head of the School of Physics at University of Melbourne, and he'll be telling us about quantum research at School of Physics and more generally at University of Melbourne. So Harry, yours.
Thank you very much. I am Harry Quiney. It's my great pleasure. Thank you for inviting me to give the talk. I'm the head of the school, but I have a bird's eye view of all of the activity that takes place in the school. And what we're going to do is to have an overview about the history of that activity and where it's all going. So in the beginning was the Centre for Quantum Computation, which is the longest running centre of excellence. I was around just in the school in 2003 when it started. The University of Melbourne made significant contributions to silicon quantum computing, experiment and theory, and various incarnations of this original centre are still running at least until 2025. I also remember QCV. QCV was an early startup in 2005 to 2008, and the V obviously stands for Victoria. It's a significant basis for the University of Melbourne establishing its diamond-based technology systems, quantum technologies, and so on. And so there's really kind of two threads, the quantum computing thread and the quantum sensing thread that came out of these two origins. Now, a particularly exciting recent development has been the IBM Quantum Network Hub, which was established in 2018 and is a collaboration between the Faculty of Engineering, Business and Economics, and the Faculty of Science. It does quantum computing at the leading edge. It uses the first generation of quantum computers through the IBM network. The network itself formally is comprised of 13 academics, 20 PhD students, and 10 billion quantum program shots. So I have a peripheral relationship with this activity. I supervise or co-supervise a student with Usman, and Shabo is in the back taking notes. A very recent development is QBIC, which is, if you can think of an offshoot from the quantum sensing work, the Centre for Excellence in Quantum Biotechnology. And we'll hear about that in a moment, but it also involves quantum sensing, computing, imaging, bioinformatics, and the interface between physical sciences and biological sciences. And of course, in the School of Physics, every other person, if you throw a rock in the School of Physics, it'll hit someone who's doing some form of quantum science, including me, but don't throw any rocks. Over in chemistry, the Centre of Excellence for Exciton Science is developing excitonic materials. The Dark Matter Centre, which is run by Elisabetta Barberio, is a collection of particle physicists and astrophysicists doing the kind of conventional particle and astro thing, but also looking at quantum sensing techniques to get at new states of matter, new aspects of physics which are not yet understood. So the quantum sensing effort at the University of Melbourne between the years 2011 and 2022, this was established, the Quantum Diamond Labs, established largely by Lloyd, and its two signature riffs were the first quantum probe of a living cell, which won the Eureka Prize Research 2013. And here is quantum sensors in a cell, and also imaging current flow in two-dimensional materials like graphene in science advances. I have to admit that I didn't write these slides. There was a change of management in 2022, and this whole area of research was taken over by David Simpson, who has been tremendously successful, actually, in transiting the technologies into applications in biology, defense, precision navigation, translation of the technologies, and commercialization. So here is our kind of cartoon of the quantum sensor, nanodiamond, or some quantum object which interfaces with chemistry, quantum dots, the exotonic sciences, biology and biological sensing, medicine, and also material science. The advantage of the diamond sensors, obviously, is that they operate at room temperature, they're cost-effective devices, they're biocompatible. Diamond is a biocompatible material, and they show great promise for being able to be tremendously sensitive probes of magnetic fields, temperatures, and electric fields. I participated with this group in one of their students, Erin Grant, who did a lot of work looking at quantum-assisted assay techniques for looking at ferritin in blood, which is an important diagnostic tool for blood diseases and anemia. And this has led to spin-off or translational applications in Phoebe technologies and also Chromis technologies. And you can see the kinds of collaborators which are interested in these technologies: the Florey Institute, Murdoch Children's Hospital Research Institute, the Melbourne Hospital, and WeHi. Now, this is a slightly overwhelming slide, but it has a simple message, actually, that in parallel with all of this, the school has been developing the techniques for silicon-based quantum computing technologies. This is led by the inimitable David Jamison over in the corner there. Of course, there's been a lot of activity, but the signature riff of this technology is silicon-28 enhanced substrates. Obviously, well, perhaps not obviously, but naturally occurring industrial-grade silicon contains about 4% of an isotope which has a non-zero spin, and that pollution of the fluctuating fields due to this non-zero spin actually cause a rapid decoherence of any quantum system you build. So the idea is actually to enrich or enhance the silicon-28, which is spin zero, in a localized region, and to build your quantum device in a localized region, which is almost entirely silicon-28. And you can see that you can squeeze out by some very ingenious experimental techniques, which David would be very happy to tell you about were he here. And annealing the substrate, you can get down to 3 parts per million of silicon-29 over regions which are about 20 micron squares. And in these silicon-28 enriched regions, you can build quantum technologies very much along the lines that you might imagine, by implanting very carefully and under controlled conditions spin qubits, either nuclear spin qubits or electron donor qubits, into this isotopically enriched lattice to build prototype devices. Wasn't me. Which brings us to the Quantum Hub, which is a partnership with IBM, which has existed since 2018. And the key University of Melbourne stakeholders in this are the Faculty of Science, it's led by Lloyd, the Faculty of Engineering and Information Technology and Business and Economics. And there's been a very rapid rise, as you might imagine, in the uptake of people participating in this program because quantum computing has gone from a glint in someone's eye 20 years ago to an actual working thing. And nothing is likely to generate enthusiasm than actually doing a real thing. You can see by the profile of the people involved in this that Lloyd is the director of this. We had the opportunity to appoint jointly with the School of Maths and Stats two extremely talented young academics, Josh Coombs and Lucas Huckle, who are actually shared now between the Department of Maths and Stats and the School of Physics. They are themselves now establishing themselves leading active research groups in quantum computing technologies. Kim An Lee Kao in maths is leading a lot of the development in maths, also in applications to biology. You can see that there's a smattering of people from physics, and also Kate Smith-Miles from maths, who is very well known for her work on optimization theory and optimization algorithms. Usman, who works in CSIRO, but works actually in the school 1 day a week and co-supervises students and participates in our teaching programs. You can see that there's some senior input from the computer science department and mathematicians and physicists, including Martin, who's in the audience, who are looking at potential algorithms and applications. And the research involves quantum information, quantum device characterization, quantum applications, and quantum machine learning. This also feeds into 5 more minutes. That's no problem. This also feeds into our education program. We have a second-year subject, and these codes represent that they're master's level subjects, which actually currently service about 200 students a year. So there is a kind of tremendous student interest in these activities. The research areas involve quantum machine learning, quantum simulation, and optimization, and they involve all the participants that I've listed earlier. And it's a very interconnected, interdisciplinary group that works in the foundations of quantum computing and algorithm development, all the way into devising new applications for quantum systems. There were Zoom issues, yeah. Don't believe so, no, but not right now. Quantum education, one of the great triumphs of the group was to develop a graphical interface, which actually has, I think, driven a lot of the interest in quantum computing. And that's a repeat. In the next slide is the flyer for something which was run by Lloyd on the 24th, which is a couple of days ago, involving 130 high school students. Remarkably, high school students, today's mission to go from zero quantum computing to quantum computing programming in 3 hours, using the facility which is embedded in this remarkable piece of software, which greatly simplifies the design of quantum algorithms. And obviously, it's a standout success with the students. The overall rating is 8.6 out of 10. For those of us who are university administrators, that's about twice as good as you ever get for any course that I teach. Finally, for those of you who are interested in learning more about what's happening at the University of Melbourne, this slide lists the poster presentations and the short oral presentations, which will be available at QTML 2024. Thank you very much.
Thank you very much, Harry. Right on time.